I'm going to switch my camera so that we can look at the parts in terms of what you have. So you should have in your FM transmitter kit, so there's the green circuit board. We're not going to use that today. There's also, I've already lost mine. There's also a wire, a really long wire. We're also not using that. There's a few parts that we're going to save for later on. So you'll need your protoboard. Oh, here's my green wire. You'll need your protoboard and your digital multimeter. And what we're going to do is we're going to build the circuits in chapter 8. So the key ones that we're going to work on are figure 8.10 and 8.15 for today. So that's the plan for today, is that our goal is to build the circuit in 8.10 and 8.15. So quick show of hands, how many people were able to watch the video that Aditi made introducing sections 8.1 and 8.2? So I saw 2 hands up. How many people were unable to get to that? Saw 3 hands. Okay, so we got 2 or 3. Okay, so with it being split, okay, so some have read the chapter. So with it being split, what I'll do is I'll share my screen and I'll do a quick walkthrough of the key concepts from that video. This will be a refresher for those who watched it. So essentially what we're thinking about is, and I should also give a little bit of, I'm gonna switch my video back. Okay, so essentially what we should be thinking about is we want to build a transmitter. So we want to build some device that's going to take our voice and it's going to convert it into a signal that can be sent as a radio wave. This particular project has special meaning to me. When I was in high school, some of my friends had signed up for an electronics class because they had heard that in the previous year, they built this exact project, something to convert your voice into an FM signal. And they thought it was really cool. And then when I heard about that, I was like, I need to get into this electronics class. And so I took electronics as an elective class in my junior year. So I took electronics 1. My friends ended up taking 1 and 2 because they were able to sign up for it. So this topic, in addition to being sort of my motivation and my entryway into engineering, was also the entryway for the grant and project that we've had that's been able to launch the summer camps in electrical and computer engineering. Back in 2008, I visited some of the existing summer camps that Illinois was offering. They were at the middle school level that we had our summer camps for. So there was ones in civil engineering, there's one in bioengineering, one in bioimaging, and one in chemical engineering, and computer science. And so at the time, there wasn't anything that was focused on electrical and computer engineering. And so I wanted to be able to offer something to excite girls to be into ECE majors. So when I was looking at what was being offered and the level that it was being taught at, I was really impressed by the challenging material that the instructors were able to present to this level of an audience. So the students in the camps were building really cool like bridges that were technically sound. They were programming, I forgot what the language that they were programming in it, but they were creating programs that were doing animations and playing games. And then they were doing work in some of the research labs building up these soaps. So for chemical engineering, they were learning how to make soaps. And I thought there has to be something that's accessible to high school students. So I wanted to shift some of the focus towards high school. So we wrote a grant to Motorola Foundation with the selling point, because Motorola is a communications company, with the selling point that they were going to build this FM transmitter. And that was going to be the central core of introducing students to electrical and computer engineering. This was back when cell phones were brand new and like very few people, it wasn't like everyone had them. And so we wanted to talk about the different subfields of electrical and computer engineering as it pertains to the cell phone. So we wanted to understand, how does the battery work? How does the transmitter work? How does the antenna work? How does the optics and the imaging work? And so a lot of the camp was structured based on the idea of presenting it as a cell phone. So this was the core project, and we were able to launch. So we received funding in 2009. We launched the camp in 2010. And every summer since 2010, we've had about 20 high school girls come to Illinois campus to do electrical and computer engineering camp. And this has been the central project of the camp. In person, we're able to do this with soldering. So this also introduced the idea of building circuits with soldering. And that was probably the most exciting and the most fun activity that the girls had. Year after year, they would comment that that was what they enjoyed the most, was actually putting together a working circuit and being able to show their parents that they can communicate into the microphone and have it sent and hear it on their radio. This year with virtual, we're doing the circuit on the breadboard. So it's less fun than if we were soldering it, but the hope is that once we've built the circuit, we'll still get the same functionality and the same enjoyment out of the breadboard circuit. And then assuming that in-person and extracurricular after school starts back at some point, hoping that the STEM club participants will be able to solder their circuit. Okay, so long-winded tangent, but let me jump back to the technical stuff. Okay, so how do we communicate? So there's sort of the wired network where you have electrical connections between the different devices. And then there's the wireless, which you're very familiar with, which allows us to transmit information through air with our electromagnetic signal. So the electromagnetic waves are what's carrying the information from the router to the computer and to your printer or to your cell phone. So the question is, why do we need to encode our voice into electromagnetic waves for radio transmission? So the simple answer is that our voice has a frequency range between 20 hertz and 20 kilohertz. These low frequency waves don't travel very far as you try to transmit it over space. So you can imagine that if I were to yell, then someone in Chicago is not going to hear me yell because the distance is too far based on the frequency of the wave. However, if I transmit the signal as an FM wave, okay, maybe I can't reach Chicago, I might be able to reach Rantoul or a neighboring community that's within a few tens of miles away, but I'm able to communicate with FM wave. So voice, we see that as you go further and further, it starts to attenuate. And so in order for us to send our voice signal, what we do is we attach it to a wave that can travel in space, and such a wave has high frequency. So this process is known as modulation. So we take the voice signal that we want to transmit, or the song or the music, we mix it or we modulate a carrier wave so that we can send it at a different frequency so that it can make it to its destination. And then at the destination end, they have to receive the wave and convert it back into the sound wave. So the two different types of modulation that you're familiar with are AM and FM. So AM means that you're going to modulate the amplitude. So when the part of the signal of my voice is high, the amplitude of my carrier is high. And when my voice is low, the amplitude is made low. For frequency modulation, what I'm doing is I'm adjusting the frequency of the wave at that particular moment in time. So we did this demo where we looked at, too many windows, where we looked at this audio application, this audio visualizer as to what's going on with our signals. So when we sing or when we talk, we remember that we can represent our voice by a sum of different sinusoidal waves. So we have waves at different frequency that carry information about our voice. This is the data wave that we want to transmit. So this wave is at low frequency. So this is at 200 hertz. The carrier wave, this is going to be at the FM frequency. So this is 100 megahertz. Like when you tune your FM dial, you can tune between 88 megahertz and 108 megahertz. So this is very high frequency. Now for this demo, we don't go that high. We only go up to like a few kilohertz, so like 1,000 hertz. And then in order for us to encode the signal, there's another parameter called the FM deviation, which just basically means how much of the frequency spectrum we're going to be using. So if I play this note, let me see, I have to share audio. So let me do this again. Okay, so if I play this FM modulation, what I've done is I've taken the voice signal that I wanted to listen to. This is my voice. I've modulated the frequency of the carrier wave. So when the signal of my voice is high, I use a slightly higher frequency. So this is oscillating very quickly. When this voice wave is low, then I use a lower frequency and I go back and forth. So high part of the signal of my voice means that I use high frequency. And so this is what it looks like in the time domain. So this is the oscillation as a function of time. This is what this same signal looks like in the frequency domain. We can see that it's made up of many different notes. And so what happens is, as I change the carrier frequency, so as I make this frequency higher, I shift sort of the central point of the spectrum. And so I get a different sound. And then as I change the frequency of my voice signal, what I've done is I've spread out or I've compressed. Let me reset this. So if I change my voice frequency, so what I'm doing is, so if I increase the frequency of my singing, like if I sing a higher note, then I'm going through these oscillations going from a low frequency to a high frequency to a low frequency. I'm doing that much more quickly. And so that influences what the frequency domain signal looks like. So with this, I can encode the voice that I want to transmit onto an FM signal. This is what I'm actually sending, and this can make it many, many kilometers or miles to the destination receiver. Okay, so I think there was a comment in the chat. Okay, you could not see the app, only the PowerPoint. Were you able to hear?
This is Dr. Coleman. I just typed in the app into my computer myself on my webpage, and I was able to do just like what you just did.
Okay, but like in the video, it did not share correctly. Is that what I'm hearing?
The second time it showed, Professor.
Oh, the second time it showed. Okay, so let me share my screen again. Okay, so all right, so resuming. Okay, so comparing AM and FM, so AM waves are typically slightly lower frequency than, slightly lower frequency than FM. So AM waves are going from like 530 kilohertz to 1710 kilohertz, so 1.7 megahertz, whereas FM goes from about 88 megahertz to 108 megahertz. So the distance that these waves can travel is different. So AM tends to travel farther. It's able to be used for news broadcasting, but the quality and the fidelity of the voice is not as good. It also has issues like if you're in a parking garage, you generally don't get your AM stations, and that's based on like the size of the garage and the wavelength of the radio wave. Whereas FM, because it has a shorter wavelength, you're able to actually hear it or receive it in your car as you drive through the parking garage. So if you've never done this before, just see it sometime. If you're in a parking garage with your radio on, you'll see a difference for AM versus FM. Okay, so now we want to build this FM transmitter. So in order for this FM transmitter to work, there are many different components that need to happen. The first step is we need to convert our voice into an electrical signal. So to convert voice to an electrical signal, we use something called the electret microphone. So this microphone, the idea is that you have a diaphragm. So you have a top plate and you have a bottom plate. And this is going to form a capacitor, and a capacitor stores charge. So when my voice hits the microphone, the top plate vibrates, and this vibrational motion means that when I move closer, then I'm going to change the voltage that's across the microphone, because the charge that's on this capacitor is fixed. So I have a certain amount of charge on the capacitor, and by changing the gap between the plates from the sound wave that's hitting this top diaphragm, what happens is I change the voltage across the microphone. So that allows me to build a device that transduces or converts between sound energy and electrical energy. So I take my sound wave, which is my voice, and I can convert it to an electrical wave, by using this type of microphone. So in your kit, it's this really tiny dot looking thing. And so inside this, there's a plate diaphragm, and this diaphragm can move up and down very, very small amounts. And then you get the output as an electrical signal onto your pins. So once you've created this very weak, and this is a relatively weak effect, so you create a very weak signal that contains your voice information. The next thing that we need to do is, for it to be practical, we have to amplify the signal. So we use a transistor to do amplification. So remember from when we talked about chapter 5, a transistor is a device that can be used to amplify signals. So the idea is that I feed in this electrical signal to the base of the transistor, and that's going to change the amount of current that's flowing from the collector to the emitter. So what happens is I get an amplified version of my sound wave, and this amplified version I can then use to drive other components. Now, this particular sound wave has an offset to it. So what I'm going to do after this is I'm going to add a few other components. So the first component, there's a capacitor. The capacitor is going to block some of the offset, and it's going to essentially shift this wave up and down. But then once I've worked with this wave, I now need to radiate that wave as an FM wave. So this part of the circuit, this is going to be the part that you're going to build on your own, or time permitting at the end of this session. This part, what it's essentially doing is it's taking this electrical signal and it's going to modulate the capacitance of this transistor. So the transistor, in addition to amplifying signals, it also can be used as a variable capacitor device. And so there's a very small capacitance that this can modulate. And then this part of the circuit, this is known as a tank circuit. Basically, it's a capacitor and an inductor. And what happens is this can oscillate at a certain frequency. So by tuning this capacitor, there's a screwdriver that you'll have to tune this. You can change the frequency that this circuit oscillates at, and you can get it to tune to a radio station within the FM band. So you can adjust the capacitor to get something that's going to radiate between 88 megahertz and 108 megahertz. And then there's additional components. There's this antenna, so it's also known as an aerial. And then there are a few other capacitors and resistors which have their own functionality, which we won't really get into. Okay, and so then that radiates it away. So what we're gonna do, so we have 15 minutes for this first session, and we'll mostly work on building this part of the circuit. The second session, we're gonna build the second third of the circuit. So this is like the first third of the circuit we'll do in the 15 minutes. The second third, we're going to spend the next 50 minutes building and testing. So the second session. And then on your own, you're going to build the sort of final third component, which goes at the output of this part of the circuit. Okay, so we want to build the circuit that's in figure 8.10. Now in 8.10, what we have at the output here, in that figure itself, there's a speaker. Because we're doing this virtually, we're not going to use the speaker. So if you see anywhere on the slides that says speaker, ignore that. That component is not going to exist. And instead what we'll do is we'll actually just measure the voltage between the points that the speaker was. So in the past, we used the speaker as an audio way to tell how strong the signal is. Here, we don't have that capability, so we're just going to measure the voltage directly. Okay, so to build 810, there are several tips that I want to give you. So the first set of tips is that, similar to the LED calculator circuit, we're going to have the circuit that we're going to be building, and we're going to label specific points on the circuit. These are going to be points that you're going to do your measurements at. These are also node points. So what we're going to do in the book is we're going to write in the book, it's your copy, so feel free to write in it. At these 3 locations and at this ground location, what we're going to write is we're going to write the column that we've plugged things into. And this will allow us, so we're going to write it next to or in our book next to these points. This will allow us to keep track of what we've plugged in and make sure that we're plugging in the circuit correctly as we build. So these points, wherever we have a node, wherever we have 2 things connected, this has to go in a unique column. So this allows us to tell that our circuit is correct because we know that we've plugged in this end of the capacitor to, or let's say this side, we've plugged in this end of the capacitor to this particular column, and we also have a resistor, and we also have the positive side of the microphone. So we're going to use the sort of node analysis and write out at each one of these nodes which column we're using. Okay, so for building the circuit, let me switch cameras. And yeah, I guess I can keep screen sharing going. Well, yeah. We'll soon find out what it records, whether it's recording the screen or whether it's recording the side video. So let me. Okay, so let me go here. So what we'll need for this first part, we'll need the microphone. So this component which was loose in the bag. We're going to need, in terms of the resistors, we're going to need the 22 kilo ohm resistor. So from your parts list, pull out the 22 kilo ohm resistor and also pull out the capacitor, which is the 22 nanofarad. So it's labeled 223. So it's the one that has two of them identical. So these are the three components that we need. We need the microphone, we need the resistor, and we need the capacitor, and then the battery and the battery clips. We're not going to plug in the battery and the battery clip until the very end. So for building the circuit, the areas that people have had the most trouble with, one area is the microphone. So the microphone has a polarity associated with it. If you plug it in backwards, it's not going to function the way that you want it to. The second challenge comes in when we do the second half session, when we start working with the transistor. The transistor also has a specific orientation. So those are the two parts that give participants the biggest problems. Okay, so I'm going to set aside the battery and the battery clip. It also helps to have a few jumper wires in your circuit. So the very first step, we're going to flip the microphone over, and we're going to look very carefully that there are 3 metal stripes that go from the center to the outside. So make sure you can find those 3 metal stripes. Okay, I'm going to pick, the other thing that comes in is that as you plug in this microphone and you plug in components around it, the outside of the microphone is electrically connected to one of the pins. And so this is all connected to the ground of your circuit. So when you're laying out the parts, you have to leave enough space that nothing touches it that you don't want to touch it. So the first thing that I'm going to do is I'm going to position my microphone. I'm going to have the 3 stripes, the pin that's connected to that, that's the negative. I am going to pick to plug this in to column 4E. So the reason I picked 4E is that it's far enough away from where I need to make my other connections that I can put jumper wires and I can still make connections. So what I've done is in this circuit, I've picked that the negative here is 4E, and therefore the positive, based on how I faced it, the positive is in 5E. So what you would do on in your book is, switching back and forth, okay. So what you would do in your book is you would label at this node, I've plugged this into 4E, and I've plugged the positive in to 5E. So you should write this down so that you keep track of where you've plugged things in. Sorry, which book? Okay, so the project-based exploration of electrical and computer engineering. So this is the blue book with the statue on the cover, and we are on page 79, Building a Radiophone, chapter 8. Okay, so we've recorded those 2 positions for where we've plugged things in, at least the microphone. So that's sort of the simple part. Once we've set this up, Now we can plug in these other components. So in your setup, usually you pick this positive to be the top rail at the top here. So I'm going to use my battery clip, but I'm not going to plug the batteries in just yet. So the positive rail is this red one, and I'm going to plug it in very far away from where I'm working with the microphone. The rail is connected, and it just gives me more space to work. Okay, so I've plugged in the red to, and I'm realizing that I have a different, it's been a while since I did this session. I forgot that I have this elevation thing to make this more visible. Okay, so hopefully you can see that better. So I have my microphone with the 3 stripes. I had that in 4E and the other end in 5E.
Can you repeat that one more time, please?
Sure. So the microphone, you have to find the one that has the 3 stripes at the backside. And the one with the 3 stripes should go into 4E. And the one without the 3 stripes will end up facing and go into 5E.
Thank you.
You're welcome. All right, so with the microphone in place and remembering that we're not actually going to build the speaker, the 2 things left that we have to connect are 3 things. We have to connect the power supply. It says 5 volts, but your 3 volts is perfectly fine. We have to connect this 22 ohm resistor, and we have to connect a 22 nanofarad capacitor. So this part I would like you to attempt on your own and then let me know how it goes. The other part that I forgot to mention is, okay, so the black end you're going to plug into the blue rail. So you have the red on the red rail and the black connected to the blue rail. You need to plug in your 22 ohm or 22 kilo ohm resistor between 5E and the rail. And you need to connect the 22 nanofarad between 5E and some other column on your board. So I'd like you to attempt that on your own. Feel free to ask questions as we go along.
Linford, could you run through that connection again?
For the microphone or for the
capacitor? The capacitor and whatnot.
Okay, so I wish I had deleted this initially. Let me do that. Shape fill, clear, shape outline, clear. Okay, so what you're building is going to look something like this. So what you want to do is you've already connected the microphone between 5E and 4E. We just looked at connecting the battery clip. So we have the positive red lead on the positive rail, and we have the negative lead on the negative rail. So what's left is we need to have a resistor going between 5E and the positive rail, and we need a capacitor to go from the microphone to some other column. And it doesn't matter which column we pick.
So Linford, I only seem to have one of these little microphone things. This is Sharon, sorry.
Yeah, so there should only be one.
Oh, okay. Because you're saying like, look for the one with the stripe on it. I'm like,
Oh, no, flip. Okay, so flip the one that you have over.
uh-huh.
And you see the side with the pins?
Yeah.
So on the pins, look very carefully. There are 3 tiny stripes between the center and the outside.
All right, that is asking for something that my eyes just won't do.
Yeah, it's kind of tough to see. So one trick, like if you can't figure out which one it is, if you place the 2 pins such that they're in 4E and 5E, they're going to face towards A. that's sort of a shortcut. If I were to place it backwards, it would have gone over the gap. So if you
Okay.
can't see which one is which, if you place it such that the pins are in 4E and 5E, the microphone will face towards A.
Okay, that I can do.
All right, Linford, I'm going to be bold and I'm going to ask a question.
Sure.
So as I'm looking at this, I'm thinking that I'm doing it right, but I'm questioning the 2NF capacitor.
The 22NF, yep.
Yep, and so a 22NF capacitor, and that's going to be, I need to have that going between 5E and 0.3, the point that you have listed there is 3, and I'm trying to figure out what that 0.3 is. Would that be my negative line, or
No.
is that
So this
okay?
this point should be any column that nothing else is currently plugged into.
Got it.
So right now it's an open connection, like it's not connected to anything yet.
Okay.
Hey Linford, is figure 8.16 in the book, is that the final layout for the radio?
So 8.17 is what we're going to build at the very end.
Okay.
8.16 is the representative figure of 8.15, so it doesn't have all the components for the final FM transmitter. So the final transmitter on breadboard, we've never done as part of the camp. We've always soldered together the FM transmitter full circuit. We've always done up to 8.15 on breadboard, and then 8.17, we've taken all the parts out and put them onto a soldered board.
Oh,
so
okay.
the final board looks like, there's a typo. So on page 86, it says 8.12. I fixed that in the updated version, but that's what the final circuit used to look like. We've since redone the circuit. And so the final circuit, based on the board that we purchased in bulk for your kits, will look something like this. So we spread the components out a lot further, and we've made it easier to figure out orientation of components. So this is sort of the final product if we had soldering available. And we're essentially going to be building this equivalent circuit on our breadboards. So half of it today and the other half asynchronously.
Do we have a picture of that somewhere? Or is that the 812, or I'm sorry, page 86? Okay.
Yeah, the one on page 86. But the form factor is slightly different, and we've changed some of the components a little bit.
Gotcha. Okay.
So I'm new, and
Sure.
you guys might have talked about this already, so please just tell me no if the answer is no. But I don't know how to think about this. I don't know what the thought process should be for me to figure out where to place these. I'm just
Nice components. Yeah. So the thought process is wherever you have something called a node. So let me show you a more complicated example so that the concept of node makes sense. So a node is a place where multiple things are connected. So like each one of these red points, you have a different circuit element connected between these 2 points. So like I'm plugging in the 1 mega ohm resistor between this one point in my circuit to this other point in my circuit. And each one of these nodes is going to correspond to a column. Now on my breadboard, so you missed the first part where we talked about how breadboards work. So a lot of this is not going to make sense. So a particular column, these 5 elements, so there's a gap in between the center of the board. So the column, these 5 elements, these are electrically connected. So if I plug something into one of these elements and I plug something else in that same column on the same half of the board, then those are electrically connected. If I do that if I do the same thing on the bottom half, like if I plug 2 things into the same column on the bottom half, that's a connection. And so each connection is a node point on my circuit.
That's very helpful. Thank
And
you.
then there's also these rails. So this red rail runs the entire length. So anything I plug into this will be connected. There's a separate red rail on the bottom. So this is also a positive connection. So I usually connect my batteries to the red and to the blue. The other thing that is important is how you orient the board. So I really encourage laying out the board horizontally so that 1A is in the lower left corner. This allows you to visualize a circuit like this, like there's sort of a top of the circuit and the bottom of the circuit. I can visualize this red row as the top of my circuit and the blue row for the negative as the bottom of my circuit. And my components can go essentially from the top towards the bottom in the same way that I go from the